Good morning, everybody. My name is Michel Mumenthaler. I'm from the company MECO. We're building clean utility systems in the United States of America. We are a global company with presence in US, in Europe, Asia, and now we are trying to technology. So first, I'd like to speak about MECO quickly. Who are we? We are founded in New Orleans, USA, in 1928. So we are nearly 100 years old. So there is a big party coming soon. And so we have 4 global offices in 3 different countries. At the moment, nearly 350 people globally. We have 27 patents on water technology, different aspects. And a bit of a bullet point is every day more than 100 million liters of purified water and water for injection are generated from MECO water systems. Get you to know us a little bit more in Turkey. The focus of today's presentation is on water for injection, WFI, and what is expected of water for injection. And then we're going to look at the latest trend, which especially in Europe, we are looking at a steep increase of membrane-based water systems for water for injection through membranes, EDI. And then we are going to look at the storage of water for injection, because if we want to generate water for injection at room temperature, we best store it at room temperature as well. It will be most energy efficient and will give you the best benefits. That I will also cover ozone generation, because ozone is an agent that we use best to protect our water for injection from bacterial growth at ambient temperatures, and ultraviolet is going to destroy our ozone, because we must make sure we don't send ozonized water into the loop to your user points. We are going to then look at the conventional methods that most of us know, distillation from multi-effect and vapor compression, and the pros and cons of each of that system. And in the end, we're going to do a total cost of ownership comparison of all 3 systems. So we can have is an agent that's generated out of water. So we are splitting water, oxygen basically, we're splitting oxygen by electrolysis and generate O3, which is a highly unstable molecule. It has a half-life of 20 minutes, but it's the best sanitization agent we have. 7.6 parts per billion of ozone kill everything. So why would we not use it in the water? Because we are used to the advantages of hot water or the biofilm after the loop, on the loop return. So on the PNID, we have our ozone generator here. This is your line coming back from your loop, from your points of use. We're going to a cooler because when we have an ambient system, we need to make sure the water remains between 18 to 20 degrees. And that is also when ozone is at its best at these temperatures. So ozone is generated from the water for injection, injected into the line, and then we go one slide back. It's coming here through this horizontal loop return. It is typically injected back into the tank with little holes. So the ozonized water is going to bubble up and fill the tank. Now, you may ask, if you don't know the ozone, you probably now ask, well, how do we keep it safe? How are we ensuring we do not send ozonized water into our plant, into our loop, and risk contamination of our products at our use points? So this is basically the beauty of ozone, is it is easily destroyed with UV lights. So it's usually 254 nanometer. Is the wavelength that kills ozone. That's why on the typical distribution system here you have your pumps that send the water out into your factory, But before it goes there, it goes through the ozone destruct UV system. That's this. So here is another ozone measurement point. That measurement will have to show 0 ppb. And if it does that, the water goes into the UV points. So how do we monitor that whole thing? First of all, hardness and chlorine monitoring is done at the pre-treatment stage. Yeah? Conductivity, which is our guiding quality metric, is measured after the ultrafiltration of the generation skids to allow the water to fill the tank. Conductivity and TOC are monitored before the ozone injection at the loop return. We also monitor the intensity of the UV light here. And we have 3 ozone sensors in the system that ensure the system is operating safely and to quality expectations. But first of all, the water comes out of the tank, goes through the tank, to the pumps, distribution pumps, sanitary pumps, and then we have an ozone measurement here, before the UV. So we know there is a 50 parts per billion ozone concentration in the tank, which is what we want, because we protect the tank like this from bacteria. After the UV, we have another ozone sensor which must read 0.00 ppb. If that's all automated. So if that is 0, the light is green, and we supply our water for injection loop to the factory. On the loop return, we come to our chiller because we need to keep the temperature stable. We then measure our conductivity, our TOC, our temperature, our pressure, our flow. Everything is measured after here at the loop return, plus also then the ozone again. And then comes the ozone generator, which injects fresh ozone, which is generated from the water for injection, and constantly injects it into the loop return. So this is always protected. Tanks are the greatest risk of bacterial contamination. So we keep that clean, basically. Now, so let's have a look of pros and cons of a membrane water for injection system. So generally, over a distillation, you spend less money to buy one. But that is just one aspect, because this is only the capital cost. You have single skid solution with an integrated pre-treatment, so it's all on one skid. Tap water or municipal water comes in here, water for injection comes out here. We operate this fully electrical, so there's no steam needed for this one. If you have steam, and you have plenty steam and you want to use the steam, we can use steam to heat this as well. Well, it's not the idea. There are some cons on membrane system too. So it does not self-sanitize like a distillation. You need to implement the sanitization cycle, meaning like every night or every week, or usually companies have their own policies and SOPs on how frequently they want to sanitize this. You have to do a hot water sanitization, and that means downtime. You will notice if you have water systems in your factories, every weekend or even sometimes every night, it means 4 or 5 hours downtime to keep the thing clean. It is requiring higher maintenance. We then look at the conventional methods that most of us know, distillation from multi-effect and vapor compression, and the pros and cons of each of that system. And in the end, we're going to do a total cost of ownership comparison of all 3 systems. That was a summary and a quick introduction to the ambient water for injection system. But I still would like to look at the distillations, which we all know, or most of us know. If not, then it could be interesting, because there's different types, 2 different types of distillation. We got the multi-effect distillation, which most of us still use in our production facilities, and there is the vapor compression distillation. So we are going to have a quick reminder of the multi-effect distillation. So typically, and this is our company, competitors might do it similarly or differently, we typically offer a configuration from 3 columns, 3 distillation effects, and small flow rates, starting from 280 liters per hour, to 8 distillation effects and 50 tons an hour. So this is what we standardized on. Customers sometimes ask for 30 tons an hour. We can build it, of course, but it becomes difficult to transport. So you can increase the efficiency of a multi-effect distillation by adding columns. But what most people do not understand or do not know so much is that the more columns you add to your multi-effect distillation, the less energy it will require to generate distilled water for injection. So for example, mostly we see 5 column, 4, 5, maybe 6 column units out there. Why is that? It is usually the price of the system. Because as you can imagine, nowadays the global pharmaceutical companies are all on a campaign to reduce carbon footprint. So net zero strategies everywhere on any global company. And one of the biggest bad boys in the CO2 footprint is the multi-effect still, because of the high energy consumption, the high carbon, high steam consumption that is required. And that's just the still. The hot distribution obviously adds to all of that. It's just one of the biggest energy consumers in a pharmaceutical production facility is the multi-effect still. Look at the alternative distillation method, which is the vapor compression still. And I think it's not so well known in Turkey, I believe. But in the US and in Europe, when water for injection needs to be distilled, so API manufacturers or bioproduct manufacturers still need water for injection to go through a distillation process, because they want that phase change of the water, so to actually evaporate it and then recondense it gives an additional safety factor, because yes, you're changing the status of the water. So MECO have actually, that's been the first piece of clean utility that MECO developed in the 1930s and then patented it, and it's ever since been the focus of our engineering, primarily because the energy efficiency of a vapor compression distillation is so much better than a multi-effect distillation. But it is still a distillation, only with one evaporator, and not several columns that every time you distill, you recondensate, you distill. We don't do that here. Also, we have. On the other hand, the heart piece of any vapor compression is the compressor. That compressor is a MECO patent. We built those in-house, so we do not buy them in. And there is the only directly driven VFD compressor in the market. And that means the energy that needs to go in there, the electrical power, is a lot less, and the noise is a lot less. So it's quite a quiet system compared to other ones which are driven by a belt compressor, industrial compressors. So we have one big advantage here is if you are asking us, I need 5,000 liters of water for injection, we will give you the right size. But if your demand or your production only needs 2,000 liters of water for injection, this just ramps down. And you do not lose water by doing that. You can do this with membrane systems. I only need 50% of my purified water. Well, yeah, then I just send the rest down the drain, which is not the idea, of course. So here, we just turn the still down to adjust the output to what you need. That obviously means a lot of energy preservation as well. You save a lot of energy. You do not waste that energy. So to look at this, for everybody who's technically interested, we're going to have a quick run through the schematic of how the vapor compression works. One of the big advantages of the vapor compression, and I show this on the next slide, is it does not need purified water for pre-treatment. All you need is softened water that has chlorine being removed, and then you can feed your vapor compression water for injection distillation. So what we do, the feed water, softened, dechlorinated water, comes in and is split. And here we already see one of the engineering tricks that we do. We are using our feed water as chilled water for our blowdown cooler and our distillate water for injection outlet cooler. So there's no chilled water needed for this one. We are using our feed water and running right through the coolers. What we do then is we go to a feed heater, basically. So here we need steam. That is unavoidable. We have electric versions that we're working on. So to a certain capacity, 3,000 liters an hour, we can offer fully electric vapor compression distillers. Bigger ones, not so much. And there's other solutions for that, like electric boilers off-site or centralized. But here, the water is already now at a certain temperature. And then we come into the decarbonator. The decarbonator removes our non-condensable gases. CO2 is one of them. There's other ones, nitrogen and stuff that's still in the water, is blown out by clean steam, which is taken from the evaporator column. We come to that later. And then blowing out the non-condensable gases up through the vent. So right here, the water now is already 99 degrees Celsius hot, so nearly boiling. Then it comes into your evaporator. So here we have a heating coil. Again, we need some steam here, or in the electrical systems, this is an electrical heating coil. And here we start distilling, basically boiling. Imagine a kettle, a water cooker. For your teas and coffees, it works almost the same way. Yeah? So what happens then, if you look at the inside, from the heating coils, the water starts going up through the shell tube and becomes steam. This is your distillation process. Inside here, it then comes over here where the compressor is only adding a small amount of pressure and a small amount of temperature increase, and the water, the steam vapor comes down here again, where it condensates in the, and I'm going back a slide, the WFI outlet here. That is where it becomes water for injection. We go down to the water for injection pump and out. Either we do not have a cooler because we want hot water for injection, 95 degrees or whatever, like we're used to, or we have coolers here to take it all the way down to the temperature we want. All our monitoring is here, as we know from any purified water technology. TOC if you want, that's an option. Conductivity, everything is measured here, and there's a block valve at the end. If the water's good, it goes to storage tank. If it's bad, it will be diverted. So that's all automated. So this is our water for injection generation through vapor compression. It's an old technology, older than multi-effect distillation, but it's never been recognized until, I don't know, probably the 70s in the pharmaceutical industry to generate water for injection. But what is interesting here is if you look at your multi-effect distillation, which is a pressure vessel. It needs pressure vessel directives. It's under a lot of pressure. This one is not. It's self-sanitizing, and we're using a lot of the heat that is coming off the system to actually reheat our water. So it's a very efficient process, but it's still a distillation. Right, pros and cons. We also here have a couple cons, but we have mostly pros. The electricity is the main driving force of the vapor compression. We need steam for the heat balance, but we need a lot less steam than we need for a multi-effect still. we have the option to generate hot and ambient water for injection from this. It is continuously self-sanitizing, and we take the advantage of the phase change of the distillate. So basically from water, we go to steam, we go back to water, so we're changing the state of the water, which is the actual essence of distillation. We don't do that with the ambient water system, with the membrane-based one. We do not have all those strong pre-treatment requirements. No purified water required, only pre-treated water required, softened and dechlorinated. And this one, it has the lowest maintenance cost of them all. So normally what we do with MECO, our customers have a service level agreement with us, so we are monitoring the system, several visits a year. We tailor-made that with our customers, but there is one shutdown service only every 5 years. Apart from that, your system is running all the time. With the membrane system, you cannot do that. They have annual shutdowns. The stills mostly annual gasket changes as well. So the multi-effect stills. There is a downside to it. It's generally a little bit more expensive. But if you would take a multi-effect distillation with 8 columns, it will not be more expensive. Then the multi-effect still will be more expensive. And the efficiency will be similar. But nobody buys a multi-effect still with 8 columns because it costs so much more. And you can have the same amount of water whether it's 3 columns or 8 columns. So the electrical load is another thing. We need a little bit more power to power this because we have less steam and more electricity. So this is a nice slide, the overview over pre-treatment versus final treatment for different water for injection methods. So what we have, this is your conventional train of a multi-effect distillation. We need a water softener, a carbon filter, a microfilter, then we need an RO high pressure pump, we need to go to high pressure reverse osmosis, we need to send that water to a tank, we have another pump stick, and then we can feed our multi-effect still. So yeah, that's that. The vapor compression distillation. Water softener, carbon filter, vapor compression, distribution. Done. So there is so much capex to be saved here. You don't need your PW system like you do for the multi-effect still. You just need a pre-treatment. And when this one here then, yes, it is more expensive than your multi-effect still. But if you can cut out your PW system, then this one is the cheapest capex, isn't it? It's logical almost. And the membrane system has your water softener, carbon filter, microfilter, RO again, EDI and ultrafilter. So, but no distillation, cold generation. So these are your upstream process steps that you need to consider when generating water for injection. Let us look at the total cost of ownership of these systems. So this analysis is a bit small, so I'm going to tell you which one is which one. You don't have to take binoculars and read. So what we're looking at is a comparison of 2 systems. One for 2 tons an hour and one for 9 tons an hour. The top one is the multi-effect distillation for water for injection. The second one is the vapor compression still for air-feed generation. And the third one is the membrane approach to air-feed generation. So what we're looking at is the following aspects. We got the capex, the total capital cost, the investment of the system. We got electricity, we got chilled water, we got calibration costs, we got quality control costs, because you will have quality control. QA will want to take samples and run to the labs and do their thing. You have water costs, steam costs, consumables, chemicals, maintenance, and labor. So all of those were compared for a 2,000 liter an hour system of each style. And what we find here is that the multi-effect still has no chance to be competitive. It's always the most expensive to run. The VC still and the membrane system are comparable But on a smaller system, the ROEDI is slightly more expensive because of the higher maintenance, higher consumables and downtime. And that we don't have with the vapor compression still, because it just runs. The fourth one is PW. We don't look at that in this presentation. The 9 meter cube an hour system, you can see the gap between VC and membrane and multi-effect becomes even bigger. Because you got the higher steam impact, higher energy consumption. It makes a big difference. Here again, vapor compression and ROEDI are comparable, but the VC still is the distillation, and the ROEDI is not. So if we're looking at the findings of these studies, these total cost of ownership studies, we have to say that utilization, how much do you use your system? Do you switch it off overnight? Is it in standby overnight? Do you actually have a standby mode over the whole weekend or something? That makes the biggest impact. So you have to be sure and say, and this has been clear for a few years now, the multi-effect distillation is always the most costly approach when it comes to total cost of ownership, when it comes to power consumption, when it comes to steam consumption. So the carbon footprint is always the biggest on the multi-effect still. Anyway, the downside of membrane systems and VC stills are that they are quite sensitive to high electricity costs. But if our power is cheap, we can go for a membrane system because we can generate it hot from a vapor compression still, and then we don't need to inject all that energy into heating it up again after we've generated it from membranes. So the whole advantage of CapEx for a membrane system over a distillation and ambient distribution goes away if we heat it up anyway. So then we better stick with the distillation. Right. So, if we want to design a new clean utility system, a new water for injection system, what are our design considerations? What do we ask first? What are our customers producing for? So, which markets are they serving? What are the products that they're making? Because different products need different head. Has anybody
Thank you.
Has anybody got a question?